Maybe we'll get started here. A few minutes past. Welcome everybody to the last TDI meetup of 2020. It's been an interesting year, and we've had a really interesting year just specifically in terms of meetups. So really appreciate everybody who's been coming on a regular basis to both the research series as well as our sort of more classic meetups, such as this one that we're about to have. As you may be aware, we will pick these back up. It'll probably be late January, February when we have our next meetup. So we're going to take a little break, but we've appreciated doing these and everybody that's spoken. Numerous people in the audience have spoken this year. So yeah, first off, just wanted to give that thanks and that shout out. For those of you who aren't familiar with these meetups or a group or me, my name is Evan Schmidt. I'm the outreach coordinator for our group, Tallwood Design Institute. I want to give a quick introduction to our group, Tallwood, specifically because the meetup that we're having today is a good reflection of what we do in terms of collaboration with industry and testing. So our group is this collaboration between two universities, Oregon State University, where myself and Ian McDonald, our director, work out of, and University of Oregon, which is where our director of design, Judith Shine, is located. And our collaboration focuses on advancing state of the art in timber research and education. And we do this through an applied research program that's updated every year with new projects, a variety of collaborations between professors and industry partners. And I really wanted to emphasize the fact that we engage in testing services. We provide testing services for anyone from manufacturers to fabricators, builders, architects, engineers, a pretty wide stakeholder base that we collaborate with on an ongoing basis. And I also want to point to the fact that we are pretty far along in getting our new lab up and running. So if you can still see my screen, you should see two images. One on the left is the AA Red Advanced Emerson Advanced Wood Products Lab, AA Red Emerson Advanced Wood Products Lab, from an aerial perspective here. And on the right is another aerial perspective of the lab from within. So you can see our new strong wall for structural testing, a bunch of different projects all lined up and ready to go. And some of our new steel that's arrived here that will be used for actually a 3-story test that Andre is involved in. Specifically, Andre is one of our speakers today. And I want to emphasize that we, again, engage in all sorts of R&D activities, basically. So those really range from structural testing here in the upper left. We have another picture of Andre here. This is from testing that was done for the framework project, 12-story project in Portland. We have a project below it that was supported by an EDA grant, looking at seismic retrofitting of buildings. In the upper right, we have a project we worked on with Kaiser and Path for their project, The Canyons in Portland, and a variety of other projects ranging from structural testing to fabrication, moisture, durability. So I encourage you to reach out to myself or Ian or Judith if you have any questions. And I think I'm going to hand it off to Ian. I think he might say something about our research consortium, and then we'll get the meetup started.
Yeah, I just wanted to thank, I know that there's a couple of people on the call today who have decided to be participants, funding members of our CCATS consortium. That's the Consortium for Engineering, Architecture, and Construction of Advanced Timber Structures. And Andre is the technical director for that consortium. And basically that's a kind of a members club that will put membership dues together and do work of common interest to try to bring more data into the US that can be used to get buildings permitted faster. And we've, if you Google CCATS and Tallwood Design Institute, you'll find a page that lists the members. We have just confirmed our 16th member today, and we're just about to wrap up kind of recruitment for year 1. So we'll do that by the end of the calendar year, and we'll be looking at our first inaugural testing program that consortium starting next year. And I would like to thank the USDA, the Forest Service and Wood Innovations Program for providing seed funding as well that will supplement the contributions of those members in our first couple of years of operation. So thank you for that. And that's really, I think, all I need to say, Evan.
Great, thanks, Ian. All right, well, with that, I'm going to introduce our speakers today. So today we are lucky to be joined by Hans-Erik Blomgren, who's a technical R&D manager. Hans-Erik, is that right, at Katerra?
Yeah, product development certification, things like that.
All right, thank you. And Dr. Andre Barbosa, who is professor at Oregon State University in the School of Civil and Construction Engineering. And you're probably aware already what we'll be talking about. If not, you're in for a lucky surprise. We're going to be hearing them talk about the development of rib floor panel system and some of the testing that was involved in getting that system developed. So with no further ado, take it away, gentlemen.
Thank you. I'll keep, just pleasure to be here. These calls are kind of, I can't join every one of them, but staying connected through these calls on this mass timber topic has been always rewarding in a variety of topics. And so thank you for keeping the pulse going here as we all work from home and leverage technology to keep this mass timber movement still happening. The format here today is I'm going to give a view on the experience we at Katerra had to deliver a product, mass timber product specific to a floor, but we designed, a building project, Catalyst building, but had a chance to really dive in and look at it from a general product development standpoint, because you know, the opportunity for doing this on one project needs to be definitely looking ahead towards maybe new systems, new things timber can do that are going to be market relevant in the US. Andre Barbosa will be talking about the testing program piece. I'll get to the outline here. And maybe everybody knows Andre, but you can introduce yourself maybe at that point on section 4. You know, and just hats off to, again, super special to give this talk to this group, because I can remember the point in time where I reached out to Andre about the need for this test. We developed a scope, a fee, and you know, Oregon State is so well positioned, and the directive from the top down to find these incremental tests that projects need to help expand wood markets. So that's why it's so fun to tell our story here. I'll say also the project engineers of record, KPFF, are on the call. So when we get to the vibration and acoustic piece at the end, I've got one slide to prompt Reed or Jack to give a summary of how they approach the analytical vibration modeling for the floors. So with that, I'll jump in. At this point in time, Catalyst had its grand opening in September, so we can now look at the building completed, even though that's not the way we had designed the product. It all happened in parallel, right? But it's a large scale, largest, I think, mass timber project in the state of Washington. Office education use, that 30 by 30 foot column grid was a key driver identified early on, where in an education building, you've got to have that 30-foot span in a bay to create classroom spaces. And then a quick study in what would be a long talk to really highlight all of the timber applications. The gravity system is rib panels and glulam, which we'll focus on today. But the lateral system, which Reed has given this group a snapshot of in the past, is CLT shear walls. The CLT floors themselves are the diaphragm. So the design method used by KPFF utilizes the strength of the wood. And there's also a cool curtain wall system. Run through a few pictures of the floor plan. Kind of a disciplined layout with 30-foot grids on the columns in both directions. The middle bay is then split with a glulam beam. So the CLT there is just a 5-ply spanning 15 feet. You can kind of see a dashed beam below, maybe over there. And then we go 30-foot spans on these bays with the rib panel. And the core wall is fits 14 feet wide to allow a walking corridor and a high bay space for building services routing through the floor. Again, during construction, a lot of wood, all ground up, super exciting to finally see a project like this through and be a small player in it all. Roughly 375 rib panels on all 5 floors. And then with the CLT panels, in addition to that, those are all, about 10 by 30 feet size. This is the first project we delivered our first 5-ply to. So our panels were defined around the first product we were going to produce, day 1, literally. So we had a 5-ply in the mix there. Obviously, we're certified now on 3 through 9-ply, but it was quite some nervous days. I was bald before I started at Katerra, but mine had gotten a little balder with some of the timing issues to deliver on this project. 50 rib panels were manufactured in our factory over 8-week span. So the production of these rib panels exceeded the erection rate on site, but it went up fast. It was all off-site built, and it's a cool story. Quickly, there's the lateral system, rocking walls, 5 stories tall, 14 feet wide, nonlinear static pushover analysis on the BRBs as the hold downs. That's item 1. The CLT floor and roof diaphragms were the diaphragm. So spline joints on the floor, Simpson strapping, collecting loads back to the core walls. The curtain wall was partially built off-site in a factory near the site. So the CLT is a 3-ply backing, insulation, rails, all pre-installed. Here's a panel going up, 2 stories tall, nice connections to the supporting edge beams, and you can see the finished product there. So again, that was a whole product level of development that, well, 1 slide. We're not going to talk about it today. Also want to, just if people aren't aware, another important thing I think we did with this project was demonstrate what a whole building life cycle assessment is for a wood building. This is an available document on Carbon Leadership Forum in Sintrafor, University of Washington's School of Forestry, developed this at the building scale. They also did a supply chain analysis of the CLT assumed in this study as assuming Katerra CLT from a production standpoint and impact standpoint. So want to not forget about that. And there you go. There's it at the end. We got this before the TI comes in. We have what we like to see here on mass timber buildings. You can see some of the building services routings integrated in here. So product and process development, coming from practice, being a structural engineer. I can remember very early on at Katerra, just kind of like, okay, there's that motivation to kind of productize things and everything we do, and really appreciating how inextricably tied process and product are. And that's kind of maybe a primary theme of this next section is, as a structural engineer, I can draw anything I want. I might know enough to know that I don't know how it's going to get built or who's going to be in charge of that. But here, you had to kind of own it on both sides of Katerra. We couldn't just spec something and pitch it over the wall and expect another group of Katerra was going to be able to build it efficiently. Continue back and forth, working collaboratively with our the manufacturing and building team. Also, I just remember this and putting this talk together that I used to work at Arup. I can remember 5-6 years ago, first time I really heard about a rib panel or this sort of build system, actually timber concrete composite in this case, but here's a building you're probably not aware of, but as we know, Europe's out in front. This is a 9-story or 7-story mass timber concrete hybrid building. And you can see here, hard to find information on this building, but I remember when Karsten from the Berlin office gave this talk once, and it really helped me understand for the first time kind of the way this can work. So, glulam members going to a hybrid glulam frame on the perimeter, concrete system elsewhere. And in this case, concrete flooring. This is the way the fit out looks. And unique to this building, these were actually precast concrete floors with holes, angled grain holes for a screw. And then on site, they put the precast down with the wood and they drilled, I guess, partially threaded screws that had already been in kind of inserted holes in the precast to create the rib panel composite action through the fastenings. So there's motivation and precedent, and it always feels good when you're doing a project and somebody else has kind of done it already. You know, you can probably get there yourselves. Also, this is commercialized in Europe. KLH has a rib element in their product line. So again, the motivation for seeing this kind of at a factory scale. We know KLH very well, good friends. Well, at some point, they weren't going to quite tell us all their maybe trade secrets on how they did this, but it left us, again, with some justification that we're maybe developing a product that's going to have a marketplace. We also tracked Clemson University. Eric Gu might be on the call, now works at Holmes. He was at Katerra at the time. And lo and behold, his PhD thesis was developing timber composites with, here I call it the Roman numeral 2 beam, but they chose this layup. You can see all the angled grain screws. This test was obviously built off of, large scale test was built off of smaller scale tests, where getting to the data to do this timber composite, you really have to understand the strength and stiffness of the fastening system you use between the underside of the CLT and the top of the glulam beam. So they did a body of good testing that got to a range of stiffnesses and load deformation curves. So when we were in our early analysis phase, we could use some of that data. I also, European technical approval, some of the threaded manufacturers do provide an axial slip modulus, KSER, which is simple math there, but gives you another way to, in an analysis early stages, get a sense of what that stiffness is going to be, so you can start proportioning your elements. Also motivated by TU Graz screw press glue composites and some adhesive manufacturers we talked to along the way in Europe. This is looking at ways you can clamp the wood together with that partially threaded screw. I believe you can maybe get 20-30 psi of pressure, and then you can put your adhesive in there, and then the adhesive then becomes the structural load carrying element, and the screw, I think the screw could arguably be removed once the glue cures, or at least it's there as a reserve capacity in the event of maybe a failure, or maybe a fire load case. If you don't believe your adhesive can hold for a fire event, you still have the protected screws, that sort of thing. So this is publicly available paper. And adhesive performance, when you start to use it structurally like this, is not an easy thing. It is heavily standardized, right? The legacy of 100 years of glulam in the US has, I don't think it's putting it down, but sometimes you learn from experience, right? So over time, the performance specs for adhesives get more and more stringent. So strength modulus, shear modulus, moisture durability, freeze thaw durability. In this case, if you can't bring the product close together, gap filling properties of the adhesives are unique, and fire performance. So you start having a lot of pieces on the table here as you try to find a way forward for something that's going to work for our project. And you really couldn't shortcut. You had to consider all of them and make sure you had something robust and a product that was going to work for the design life of the building. Again, on this project, we, because of the factory sort of, instead of a 3-ply, we really started with 5-ply CLT panel. And these pans span parallel to the glulam beams. That's also an early move that isn't first thought of. You usually lay the the panel transverse to the beams, but now you get more of the CLT section working for you as a flexure element. We had a 5-foot module, Acoustomat, and topping. So again, the structure is the wood. This is all non-structural toppings to give you maybe enough mass for vibration and the acoustic separation. Modular offsite, efficient use of wood fiber, lightweight. These are kind of the rough numbers. If you're going to be a steel composite system, concrete, and wood. So lightweight is an attribute. And we got to 30 feet, whereas a 5-ply CLT would be hard pressed. At least the 5-ply we used would come up short of 20 feet for sure, 15 to 20 feet, somewhere in there. And because we used a good composite action, we got a great span to depth ratio on par with steel. So that allowed us to bring the ribs up tight and let maximize floor to ceiling clearances. We still did get a hole through the beam allowance for sprinkler penetrations to run transverse, a 4-inch diameter hole. And the stiffness is king here. You'll see that. So the composite action we got with that shallow depth was met a stiffness criteria. And I believe through 1 hour char rating, you could do the math on this panel, and it works at 1 hour. The project was actually heavy timber, so for permitting we didn't need to directly justify that. So the criteria with code references are all shown here. I won't dwell on those too much. This piece, though, became the final performance criteria piece once KPF finished their design. Performance specified this product out to Katerra Engineering. I was the one who kind of stamped this as a performance specified engineered product that in turn went through shop reviews and was reviewed by KPFF and submitted through permitting, like is kind of a common practice for a lot of structural products. And this magic number, which just fits this project, was the minimum target stiffness we needed to achieve to in turn know that KPFF's vibration analysis was met. A lot of text on a couple slides here. I don't usually do this, but really capturing why testing, it can be, well, I'll step through my points here and maybe the point will come clear. I really think this is the first application of this kind in North America I'm aware of. So let's know what we're doing with some data. There's no defined method in the IBC. So how do you actually design a composite T-section? You can't point to a design method in the code. Chapter 1 of the IBC talks about alternative products, alternative materials, and alternative design methods. So we didn't have a way to design it, maybe in the NDS. We want to just, again, test this so we know it works and we can stand behind it as a product that's going to meet the intended life span of the building. Appreciate behavior, stiffness, creep gets measured, as Andre will show you here. And get good correlation between our model, which we did have, and testing results. Adhesive itself that we used wouldn't necessarily be classified for this use. So let's build it into a test so we can product test it. And testing services evidence for approval. And this is that little piece of the code, chapter 16, it's there, but maybe you've never noticed it. There's a pre-construction load test in chapter 17 of the code. And this is when and why you should use it. And I'll make a point that when the code is a minimum and it says shall, it's kind of hard not to wriggle away from that. So we went for it because we're also motivated, again, doing this, leveraging this story to future projects. Quick analysis, this is kind of when you have bottom up, if the two panels aren't fastened together, you get larger deflections and you get slip between these two layers, CLT and glulam. Then you start adding stiffening elements, you're somewhere between the two, and when you're fully fixed, you get full composite action. And this changes for our project, this changes the stiffness and strength factor actually on the order of 4. So all of a sudden for the same wood fiber, you can get that much structure or that much difference in performance. So efficiency starts to show up. And in Eurocode 5, there is a provision for the gamma method to have a closed form calculation method to work with. Quickly too, timber fastenings, strength versus stiffness varies greatly. I'll bring this up though, because glued joints are strong, stiff, but brittle. Doweled fasteners are weaker, more ductile, and axially loaded screws are kind of classified in here as well as something that's in the middle space, but quite a difference here on the slope, right? If stiffness is king for your design, you can still see quite a difference qualitatively here in this diagram. Using the gamma method, this is the stress profile for angle to grain screws at 6 inches spacing. This is the adhesive option we looked at. This is screw spacings at 3, 6, or 12, 6 and 3 inches on center. So, and this is kind of the sliding dial. If you just push your connection stiffness from no stiffness to fully composite in a log or semi-log scale here, you get to compare what composite action can be achieved for a given cross section. And this really led us to the adhesive as a candidate that we wanted to pursue. Screws are not free, they cost money, they are not easy to install. This assumes 30 degrees from horizontal. And yeah, it was a choice was sort of made from that process standpoint, cost standpoint, and just efficiency of the whole cross section. Even squeaky floors, is you wanted to almost put an adhesive in there to make sure you didn't have squeaky floors. And once you do that with the screws, then is the adhesive carrying the load? So we migrated with a lot of internal debate on where to land there. Quickly, I did this for this slide. The second one from the top is where we ended up on this project. I show kind of the volume ratio of 1.0, L over D of 15.5, and 90% composite. And this would be to match the same stiffness over here on the left. We would, if we had 0 composite action, the depth would have increased, to 32 inches. With the 30-degree screws, we probably would have been closer to 27 inches. And then if I were to do this again on the next project with some testing justification in our hip pocket, really a 3-ply panel is a great candidate here. You could reduce the wood fiber by almost 25%, match the L over D by making your glulam a touch deeper, and you get something better. So that's a little nod to seeing this execution, but looking to your next project. Then we had the fun of going to the factory and getting agreement with the factory. They use their space and talk to the people that are going to commit to writing the procedure and plans for doing this. We had 2 candidate adhesives and the screw press glue option at that point. One is actually a listed commercially available PRF kind of resin. It has gap filling capabilities. I made sure my friend Josh here had his hazmat suit on because occupational safety issues would require this as a ventilator. So that was kind of a point against this. It was great for the factory folks to be engaged in this because we also then looked at commercially available bead extruded high viscous adhesives. You'll see a conventional, this is what we could buy, a construction adhesive at the time, but it kind of met the principles of what we were going to do. We ended up using a little higher performance adhesive, but it got everybody hands-on, screwing it down, watching it squish, taking it off, and getting some of that feedback. This adhesive is, if it flows, it runs down the side of the beam. This had to be an architecturally exposed solution. How are you going to clean that up? Cure time, all those variables of process and amount of effort it would take. It was clear at that point that the factory folks for this project and the processes we could put in place were going to strongly encourage us with a little, way factory folks are. They in no uncertain terms, this one wasn't going to be viable. So even though maybe it was easier to justify technically. So I could have specified this, but I would have been ignoring the appeals from the people that actually had to build it. We did some work then. Washington State University did small scale center point bending tests with those 2 candidate adhesives. I don't want to dwell on this too much, but this was another key piece of building this up, where we wanted to justify what the modulus of the adhesive was and what its strength was at this small scale before we built up to the big testing Andre did. I mean, it's so valuable to get some of this data. So off these data sets and that test method, we were able to show the orange dots here show the with two of those stickers together on that bending press with no glue, so you get a low modulus. Each of the stickers were tested and you get kind of the full modulus. So the green dots represent kind of the modulus of a solid piece of wood. And both of these resins ended up, I have another summary slide of the average, but you can kind of scan across this and see that the average is about to say 85 to 90% full composite is what was achieved, and both resins or both adhesives were comparable. So that was a great point to trend towards the one that was going to be preferred from the factory process standpoint. We also did shear block testing of the 2 adhesives, and again, they were very comparable, impressively strong, because the in-plane shear strength of SPF wood is a roughly 1200 PSI. So the strength of these resins came very close to the strength of the substrate, which is, again, where you want to be from a maximized efficiency on the adhesive. So then we got into building 6 prototypes. This is crazy. This was May, 2 months before the first panel went up. So this is where, again, we were moving fast to deliver to a project on time. And we built a process, we engaged with labor on site. And here we could apply glue to 2 glulams on roll cases on a motorized roll case. We could at a glue station to apply the glue in one pass. And we had master carpenter here, Olav, who's was essential to being kind of the foreman for this project, and then overhead crane access and also conditioned space. Here's a picture of the glue spreader going down, the screwing process. This is the kind of bead you can get versus freehanding it. Super cool to get it down to 6 beads at once. And pretty simple once you get a good plan in place. Quality assurance was key. We did daily weighouts of the adhesive on craft paper. Temperature, humidity controlled was monitored in the factory. We were on the clock. I think we had to press within 20 minutes. They're going to get the panels in within 20 minutes to be on spec. We could also validate that the spread of the glue was good, again, through some QA testing to prove that the clamping force of the screws would press the glue out. Squeeze out was actually a good indication that we were getting good glue spread, and we limited gap sizes. And we also surfaced some of the wood where there might have been some deleterious material or rough spots or staples and all that stuff. So we had good mated surfaces for gluing. And I like that picture kind of gets to the cross section and the profile, and really does for a 30-foot span and a span depth ratio as an engineer, it kind of looks good. It looks about right. I don't know if other engineers kind of feel that as well, but you can sense this is an engineered product that needs to use the double T shape here to work. And we took 3 of those 6 and shipped it on a truck down to the Oregon State Lab, which is where I hand off to Andre. So Andre, your microphone's on?
Yep.
All right, destructive testing.
Great. Yeah. So so thanks everybody, and hi everybody. Andre Barbosa, structural engineer and associate professor here at OSU. And specifically with this project, we were very happy to participate in it, and in a way, like we've been in many other projects, lucky that there's so much going on in the Pacific Northwest, and we have such great collaborators. So we did take those 3 specimens. Here is this first slide where we do show our test specimen elevation and setup. I do want to acknowledge very quickly just a couple of folks. So first, Chris Higgins, another structural engineer out in our structural engineering lab here, who's been really pushing and moving forward our lab in general so that we can test something like this. And then we have 2 amazing technicians that just make things work in the lab. We couldn't do all these testing without them. These specimens were, as Hans-Erik was mentioning, 10 feet by 30 feet nominal. So the cross-laminated timbers with the 2 rib panels. The loading frame that you can see here in elevation, it's a pretty large steel structure, a 500 kip actuator there in the middle with a 30-inch stroke. And I'll talk a little bit more about the ends there. But each specimen was tested in a simply supported configuration, so with 4-point bending, and where you have the transverse beams there, you can see where the loads are being applied and being pushed down. The actuator was mid-span, and so by symmetry, we know that statics would work, and we would get our loading in the right places as we would want. But we had that stiff longitudinal beam, pretty large stiff longitudinal beam, to transfer the forces over and then down through the transverse beam. Next slide, please. This is a photo. So those 30-foot long panels taken, this picture taken as far as we could out in our lab, but you can see for scale, the gentleman there in the middle, Jeff, is about 6 feet tall. And so that gives you an idea of the scale of this, and the whole test setup and then the room, that we have here in the lab to do this. But yeah, we did in total test 3 of these. The first one is what I'm going to focus on in terms of the results that we're showing here. Next slide, please. Yeah. And then on the next one here, we can see a more detailed view from the northeast of our specimen. And on the right figure, you can see the transfer, the loads being transferred through that point where we have the rollers. That's exactly where we're transferring the load. So, we did have, looking at the figure on the left again, we had those steel supports, but above the steel support, we had some wood blocking to simulate what was actually in the field, which is, your rib panels supported on glulam beams as well. And so we wanted to make sure that we had enough room for the instrumentation, but at the same time to simulate that end bearing condition there. Next slide, please. If we zoom in a little bit more, just to show, especially here in the middle, as we were putting this setup together, we wanted to make sure that we did allow the ribs to rotate relative to the steel beam here. The steel beam is just there as a support and should not be, impacting the capacity that we're developing in our system. And so just simply support it there. And then there's that little bit of an overhang on the blocking, which is that panel sitting on the steel beam. You can also see on the figure on the right, that blocking that shows where the CLT from the main ribbed panels we're sitting on. Okay. Yeah, next slide. So in terms of instrumentation, we had for specimen 1, and Hans-Erik already mentioned a little bit of the schedule we were working with, but it was good. We had things planned out, and I think it worked well in terms of receiving the panels and as quickly as possible get out a test report, because the construction site was ready to go for these panels. But so we had in total 16 channels, 16 string potentiometers. Those six of them were measuring the vertical displacement of the ribs relative to the strong floor. And then we had 8 specimens just measuring relative motion between each of the 4 ribs, and the steel supports relative to the CLT blocking and the strong floor as well. So we could track, any relative motion near the support. You see, there's a lot of instrumentation near the support so that we could capture any of those measurements and then take the deflections, and the deflections being the motion in the middle minus the motion of the supports. The actuator, we also had channels for the actuator and the 500 kip load cell there. The instrumentation for specimens 2 and 3, we're not showing here. We had some additional instrumentation, also trying to look at shear flow over these specimens. But in the interest of time, we're not showing those here, and we are working now on a journal publication, and also we'll be incorporating those results in that. Next slide, please. So the test protocols that we used. So first, we had quasi-static loading. As Hans-Erik had mentioned, this IBC section 1709 pre-construction load tests, that includes defining a target reference superimposed design load. And that's in accordance with the initial design requirements and the building occupancy that is for this building, but also the deflection limits that Hans-Erik also showed that table initially. So those were also defined in accordance with the design requirements. So our loading protocol had 2 parts. One, which is this one, that's mainly tied to checking IBC section 1709, where you do this force control test. You will first increase the load to 2 times this reference design load. And then you have to hold that load for 24 hours. Then you stop the loading, make sure you have the deflections then, and then you remove the loading. And you need to get, and the test is deemed complete once you get at least 75% of the midspan deflections recovered. So that's that creep component, that immediate creep component that Hans-Erik was mentioning. And so that's per IBC section 1709. Once that test is complete, that was what we had to do, to make sure that this was a viable product. Then we also did the displacement control test to failure. And there we increased the displacement, regular but slow rate until we saw the drop in load. And then we could track how the specimen is failing all the way to complete collapse, just so that we have that engineering data as well. We also, it's wood, but in general, keep track of moisture and temperature. And here so if it was needed, in our lab, and it's a really controlled environment, so not as much variation of temperature, but we did check the temperature at beginning of test at 8 hours and at the end of the 24 hours, just to keep track of that. And we did the moisture just at the time of testing. Next slide, please. Okay. Yeah, perfect. So on the figure on the left, you can see that initial force control test where we are here showing the deflections of the west rib and the east rib. And as we push on, however symmetric we want things to be, either through our loading, but, things were centered with respect to the specimen, or just small variations in material parameters. So there was a very little difference in terms of the deflections that were measured initially in both ribs, but overall that difference, here the deflection is less than, or less, what is that, 0.04, 0.03 of an inch a difference in terms of deflection, but we could capture that difference in deflection. So went to that 48 kip level, and then we held the load. So now you look to the figures on the right, and you see that the load was maintained for 24 hours. And when I started doing this, I did not know that 86,400 seconds is 24 hours, right? I went to do that check. I remember the 3,600 number, but I didn't remember the 86,400, but that's what it is. The time here in this graph is in seconds. And you see, starting with the one on top, you see that both the deflections in the east rib and the west rib, they increased and they tended to stabilize after 70,000 seconds. And the load was maintained constant. So in total, this was varying between 48.3 and 48.4 kips. We had to have a load that was above 48. So that's where we stopped our test. And this was, at most had a difference over 48 hours of 100 pounds. And that 100 pounds was not because I stepped on the panel, because that if I were just 100 pounds, that would be, but it was about half of me. That was the range that was changing over the 24 hours. Next slide, please. Then, we unloaded, we checked, and we did get that it bounced back 85% of the deflection. So more than 75% of the deflection. So you see there in orange, that initial deflection post 24 hours. So after we've removed the load, that's as much deflection as we had. So we had recovered, the test was deemed successful, but then we moved on to the second part of doing this displacement control test to failure. And so if you click one more time, please. And so a few interesting things here to note. The specimen, you can see that the peak load was there at about 144, 145 kips. Based on this load, that corresponded to assuming a uniform loading over the test specimen panel area of about 450 PSF, so pretty large load. During the test, just some things to note that we noted during the test. At about 75 kips, we did start hearing some popping sounds, but those were really just adjustments of motions of the screws connecting the CLT. But if at 75 kips, if you look at the figure here on the left, you see no impact in terms of the global stiffness. But we did hear that in terms of as this load kept increasing. But it had, as I was mentioning, no impact on the stiffness. The resulting, you can, just based on this graph, you can get an idea of what that average stiffness is. But if you do take between 10% and 40% of the peak load, which is often done for our lab tests, you get about 69 kips per inch of stiffness for this 30-foot span. If you do calculate that, what the corresponding EI effective is for this loading, that's 49 million kips inch squared. Hans-Erik had showed you that number of 40 million. We got 49 million. So it was more than that design requirement for that footfall vibration. So we were above. Peak displacement at that level there is about 2.15 inches of deflection. After that point, immediately after, you see there's these squiggly lines, both the orange or red, I don't know how it shows up on your screens, and blue. So the blue is the east rib and the orange is the west rib. So at that instant, the deflection on the west rib did increase. It increased to 2.55 inch, but there was the west rib actually reduced deflection. So there was a shift in load as the load decreased. That affected how it moved. So really getting into the nitty-gritty of the testing here, and that's this is still at green. So you can see on the bottom right there is a white line, so you can barely see it, but that's the total deflection. That's what, from the white line down to the specimen on the right there, that's what 2.15 inches looks like. And this was the after failure. So you can see this was a tension failure, and it started at an end joint of a bottom lamination in the east rib. Can we move to one more click? We could have stopped the test there, you know, and if anybody's tested with me, they know I want to keep pushing until we really, really break it, and we can't break it any further. And so that's what we did next. We just kept pushing it, and it did take over up to, you know, 3.5 over more than 3.5 inches before you saw this here, which is complete failure of the east rib. All right, but in that middle section, you can see at the bottom, that's where failure started. So tension failure in the bottom lamination, and then as that propagated up into the beam, it did end up passing through where we had the hole. But you know, it had a tension failure and the hole for the whatever other utilities would be going on did not really impact that failure there. Okay, next figure. Just to wrap up, so just what happened near the end, at failure, we did not measure any noticeable slip on the south end. We did have, next slide, please. We did have about 1/4 of an inch of slip on the north end, right? But, you know, if you look at the right there, next to those holes that were there in the blocking, you can see that that's the total distance. It's less than that 1/4 inch that we had initially of an overhang between the blocking and the steel beam. That little hole there is just under 1/4 of an inch total for slip. Yeah, I think that's it. Summarizing, we did perform that test according to 2015 IBC section 1709. Results show that we recovered 85% of the deflections after the 24-hour load, which exceeded the 75% minimum. I talked about the 450 PSF. That was about 2 times the typical office load or factored load. This high margin on strength versus capacity was predicted, and it was because vibration, that footfall vibration, was controlling the design. So, you know, we were stronger there, but that's because of what controlled the design. The 49 million EI effective on that second to last bullet point was greater than the 40 million kips inch squared. And so we met also all the service deflection limits based on the testing. So from our end, we could pass on the baton, and Hans-Erik could put his stamp, right, in terms of everything was good to go. I think you're taking it from here, Hans-Erik.
Yeah, thank you. And that margin, it came out to save us later, a couple months after permitting, we had one change order of a rooftop mechanical unit. So anyways, the rib was fine as is, and that got the load up to almost 80% of utilization, I want to say, instead of this 2.5 factor. So again, future projects, or as Hardy Cross says, you know, strength is essential, but otherwise you don't worry about it. I mean, this is the point of really wanting to understand what the strength of the panel is, even though vibration really controlled the proportioning of the cross section for serviceability and vibration. All right, let's see here. Vibration and acoustic performance. Reed or Jack, are you guys on the call? I want to impress about the work that went in. The building wasn't built yet. We hadn't stood in it yet. And a lot of engineers will speak about their concern for vibration. So if you guys have a couple minutes to speak to your diagram here and a little bit of the approach, it would be helpful.
Sure, yeah, I'll talk. This is Reed, hey everybody. And Jack's also on the line in case in the likely event that I missed something, Jack will step in and correct me. So yeah, thanks for showing this diagram. I think maybe taking, pun intended, a step back and talking about how we sort of approach vibration evaluation for catalyst, and specifically setting that EI effective for the ribbed panels. This was sort of our first undertaking in sort of extensive mass timber, an extensive vibration evaluation of the mass timber floor. And so we, I think, learned a lot from it alongside Katerra and OSU. And what we ended up pursuing, this graph that you're showing is essentially vibration, the acceleration value enveloped over all possible walking conditions. So we looked at in kind of the areas where the rib panels existed, which are on sort of the top and bottom of the screen there. We looked at a slower walking pace within those areas due to the occupancy, and then a faster walking pace in kind of the corridor areas, as you would sort of expect. People can get up to a little bit faster clip when they're walking in those areas. So this envelopes sort of all possible excitation and response locations, sort of creating somewhat of a heat map. And to a degree, we're essentially using a finite element method or finite element model that is specific to the determining or assessing vibration. So it's independent of the finite element model that we use for lateral design and the one we use for sort of more typical strength and deflection checks. So in the end, what it comes to is essentially iterating on what that EI effective those rib panels needs to be to meet our acceptance criteria, which was for the classroom spaces, 0.5% G. You're seeing in that as kind of that central area, a little bit higher than the acceptable performance. And that's actually not an uncommon thing in vibration evaluation, is having peaks that are slightly above the threshold that you set. So overall, I think very interesting way in working between the manufacturing and the product development that Katerra did to meet performance specification.
Yeah, and if I can add anything to that, Reed, say that these mass timber floors is not uncommon that with a large 30 by 30 grid, the vibrations control a lot of the design just because of the lightweight nature of your mass timber assembly. You need to beef up the stiffness factor in order to compensate for the lack of mass. So the rib panels were very stiff. It was a great way to get us to a target that we were hitting.
Thank you. We again were provided then opportunity to do field measurements. And we were out on site 3 times during construction. We captured data. I guess that would be this picture here. You know, the rib panels are down, but there's no gypcrete or finishes yet. So we found a spot where there were no construction materials and looked at just that level of data. It's always good to build up your story. And we captured fundamental frequency, or more than that, but at least the fundamental frequency, damping, and then did this response factor evaluation that to start comparing to the building. With the help of others, we've published a World Conference on Timber Engineering paper. If you look at the date there, the conference happened in Chile in August, but it never happened due to the virus. But the papers are in, so I'm sharing it to people who want to see it. I think we'll get a chance to present on this next year in Chile, but I don't want to wait on disseminating the findings. Anyways, one chapter in there at the end, our section is on this, where we captured the vibration performance and frequency predicted versus measured. Getting close to 8 hertz. We also have not done, but there's going to be the final fit out where actually some walls are in the space, and the desks and the chairs are in the space. So we need one more measurement's key. So these are sort of trending towards the final built structure. I have been in the building though, and in October, and I'm 98.9%. I mean, it's such a good feeling to feel how awesome the floor felt. High frequency, rigid, solid. There will not be occupant complaints in this building. And we had a very aggressive design, I'll say. We didn't go the conservative route on anything. We kept it lightweight, kept the frequency up, shallow, span depth ratios. There's data here. You can read the paper if you're interested. We've also have product testing on our CLT done in the lab environment with companies like USG. Maxon, a month and a half ago, just paid to go out and test the floor assembly because they used their gypcrete. Maxon gypcrete and underlayment was what used in this project. Early numbers are in this range. Maxon's, again, I can get you connected with Maxon if you want to find out more, but it's cool to see Maxon go out and test this because there's just thin data out there on field measurements, right? And again, we were a little above the target for the project. And now that we know more, I'm ready to start using like a thinner 3-ply instead of that thicker 5-ply, and we can still get to adequate performance targets for typical office buildings is kind of the motivation. Quickly in conclusion, kind of big picture, I think where I'm at 4 years of Katerra is really, and the codes and standards are getting there better. It's like, you got to use CLT for what it's there for. It costs money, and if you use CLT floor panels as the rib or a bare panel, get it there for the strength, deflection, fire rating, even that diaphragm. If you can get one product to do 4 things, that's pretty good. And then you're in a place where you are supplementing the finishes for maybe vibration and acoustics, some mass and the acoustics and the underlayment, but you aren't mixing the two. And there's an efficiency there is kind of my point. So that's where we've demonstrated that on Catalyst. I also created an estimated span range, looking out ahead, where whether it's a floor or a roof, 3 and 5-ply, 5 to a little more than 10, maybe a 9, 10 to maybe up to 20 for a 5-ply solution. 7 and 9-ply don't give you too much bang for the buck. They're kind of diminishing returns if you start to look, but they also are a lot of wood mass, so you can't just throw thicker CLT at a span issue. So, I mean, look at that, man. I'm saying we can go out to 60 feet, but so from a view of 3 to 5, once you're beyond 5, start stiffening it with ribs. I don't see why you couldn't build out this product into much longer and larger spans. We need to have some projects and some work, and we have some data, we have a model, and we just need to meet the scale of the next project in those spans. 60 feet is the longest panel we make at our factory, so I did have to cap it at 60 feet. But thanks everybody. I think that kind of covers it, and I wanted to finish with this slide because it was quite an experience to pull this off on the Catalyst building, and the team and people and pride and all that good stuff. We did it. So thanks to everybody too, not pictured in this photo.
All right, great. Thank you, Hans-Erik and Andre. We'll give you a silent round of applause here through our emoji settings here. At this point, we will open up the floor to general questions. We have a couple in the chat box already, so I might just start us off with one. And after that, feel free to just jump in directly and ask Hans-Erik or Andre your question. So this first one comes from Lek. Speaking of 3-ply, he was wondering how that would affect fire ratings for the building if you went for a 3-ply rib panel system.
Well, always starting with the scale of the building. There's some beautiful structures out there, office at 1, 2, and 3, I think even 4 stories. You can do a lot at 0-hour fire rating. And then if you're at the scale of this 5 or 6 story office building, you can do a lot with type 4 construction, which prescriptively says you just got to meet 4 inches minimum for your floor plate. So you are not beholden to calculating the fire resistant rating. We did calculations, proportioned this out, and it would work at a 1-hour building. And I guess at a 2-hour too. The cross section here would not be sufficient for a 2-hour. So the other thing I guess to add, the other fire thing is also, I believe potentially with a 3-ply where the 2 long layers are going with the girders, it's that transverse 1 layer that is actually protected by a 2x or a 1.3H thick lamination. So arguably you might be able to get a 3-ply to work for 1-hour fire rating. But got to think about it harder because most of that middle lamination is left in a fire event. So that's really, again, pushing the product as hard as you can. I'd love to go and try to demonstrate that on a test it out, but haven't gotten there yet.
Good, thank you very much, Hans-Erik. So it looks like up to 4th floor, the 3-ply with the ribs should be fine. Above, you will still have to use 5-ply, right? Or additional.
Up to, a 6-story office building, T3 or Katerra's, we did 5 stories, but you can get up to 6 stories. If you're type 4, there should be nothing requiring you to calculate the fire rating. So I would be open to a 3-ply on that solution. Again, I'm reminded of where we were 2.5 years ago. The acoustic consultant hired by the architect, we didn't have actually a lot of acoustic data. So they were crying uncle a little bit or concerned about, I don't know why I use that term, but an extra thickness of wood was acoustically deemed a good idea, even though we're going to still have, gypcrete on top. But I think we have more data now to really hone in on a market rate office building, and code requirements. I think you could get there.
We got one from what was the fastener spacing that was connecting the panel to the beam?
Yeah, we didn't really spend too much time getting the fastener spacing optimized. I think we were 12 or 14. I don't think we got out to 18 inches on center. Again, that TO Graz paper had some justification for how far to put the screws out to still get sort of an even clamping force, what that pyramid of pressure from the head of screw out to the bonded surfaces was. So I think we played that a little conservative, probably 12 inches by memory.
I'm going to follow up on that. So you mentioned that this was one of the first, if not the first, applications in North America, and that KLH had developed a system like this. So I was wondering how much of your own research and development process was based on precedents, and maybe you could also speak to a little bit of the sort of health of the state of knowledge transfer from Europe and other innovating regions to other regions. So it's sort of a broad question there, but.
Yeah, fair. On the KLH piece, it was pretty clear. We again know those people, but they weren't going to let us in that part of the factory and see the process. So piecing it together, that TU Graz paper, which came out at the interconference, is really the best kind of, I think, public dissemination. We had conversations with Henkel along the way that claimed they had, relationships with customers trying to develop this product, but pretty quickly, those people aren't telling you what and how and why they did it, right? We were definitely left to, figuring it out on our own. So that Graz paper wasn't publicly available when we were in the process of our product development.
In terms of, I mean, you had a diagram early on that showed the different properties between, you know, like a resin and then using screws and dowels and the sort of various stiffness and then ductility properties you got. How much sort of work went into choosing your approach, or was it just obvious that you wanted to go with resin because you could get that high level of stiffness?
No, I think it was turning the corner to get to an adhesive once the target for vibration became key. The time and effort to put those angle to grain screws and realizing they couldn't get you up to 100% composite action, you know, constructability wise. And so then it was a matter of finding an adhesive, and that whole experience of working at the factory, that was challenging because again, you can spec an adhesive that is out in the marketplace and would make the engineer's job easy to spec it, but the process we could put together for this project wasn't there. So we found this other adhesive, and I don't know, on the back end of executing it, you know, it worked really well, right? And we did all this testing. So let's, you know, that viscous bead adhesive that had strength. Some of these construction adhesives are on the spectrum of being more like a silicone caulk, right? They're really low modulus. And so we had to parse through a bunch of construction adhesives, and we found one candidate here that the data showed looked as good, strong and stiff as a PRF. So for this project, we went with it.
Thanks. There is a question here asking if there were any vibration tests that were done prior to install in the factory, or I guess possibly with any other partners.
No, I guess we got, I mean, in hindsight, we never took a rib panel and just put it blocked up on supports and did a bare panel. We only got to that level when we had panels out in the field. And as the floor frequency is a function of the rib panel frequency plus the girders it's supported on, right? It's like springs in series. So if I go back quickly to this slide, by calculation, the rib panel only with no topping is way up here at 12.5 hertz. By the time we did calculations, which we did compare against measured, rib panel plus the girder contribution, we got good correlation and good correlation. Part of the, you know, the overall response, what really matters are these response factors. That's where you're really going. And, you know, you have to build out a pretty big floor plate to capture all the things that influence the full fit out, right? So we didn't really have the ability to do, even if you built a few up on blocks on girders, you couldn't really say this works already, right? Because we were very, the philosophy was we had to get the whole building built to really do the final assessment.
Maybe I would just mention that Reed Zimmerman did share a screenshot on the chat, which is of the SAP model, the SAP 2000 model that they use to do the vibration analysis. So there is that, that you can try to predict before you go to the factory. But yeah, just as you're making decisions on what size and how to come up with those numbers, that magic 40 million number.
Yeah.
Keeping squared. Yeah.
Yeah, and vibration, you know, there's there's a percentage of the population that's more sensitive to these things. I kind of want, after a year of occupancy, I want to, if I have time and have the time to do it, you want to go back and see if anybody has occupant complaints. That's things I've seen done on other research projects. And then anecdotally, you know, everybody can be a doubting Thomas on this call, but when we all can go and travel again, everybody else should go kick the tires on that building and feel it for yourself. It's super valuable to get these built projects built so people can experience them You know, Plat 15 is another significant project, it's pretty big spans. PV Hall, your building has, I think, 40-foot timber concrete composite spans. So, you know, these built precedents are going to be very helpful to get the engineer, I'll put it on the engineer, confident and get more economy in the floor plate designs, let's say. You know.
Got one from Charles Stark here. So I guess from some of the earlier photos that were shown, they commented on that the manufacturing of the rib panels seemed to be pretty labor intensive. So the question is if there is a more automated approach, maybe anywhere else in the world or maybe in the future, if you guys have thought about new ways of doing this.
Yes, I think to move on, there's that building a better process. Absolutely. I would say the labor intensiveness was, we cranked out 50 a week for 8 weeks, man. It was impressive to see how they went together. And the number of people on working the system was not this money. That was during prototyping where we had a lot of people kicking the tires on it. I could try to follow up with some of the more metrics on that from a build standpoint. But, you know, another question always comes up about a product report, which I'd love to do. But I just, you know, one project's not enough to have the whole business case in place, right? You got to go piece by piece to build out or see the market, have people believe in the market. And then you know, I think we could do a product report based on that code provision. The evidence submitted would be testing, short of anything else. And you could get maybe a third party to start to write you a code report using that guidance, and that could help streamline permitting, absolutely. But 1, 2, 4, 8, 24 projects, you know, it's gotta happen like that. So that's my best answer, Charles. Thanks for joining.
Yeah, and feel free to ask a question directly. You don't need to put it in the chat if you want to just ask Hans-Erik or Barbosa or Andre Barbosa directly. I might ask you guys sort of more generally speaking, you know, now that we're on topics of thoughts on the future, you mentioned pushing towards 3-ply, that you see there could be some advantages there. You also mentioned longer spans. You have any sort of just general thoughts on future projects or future developments for this technology other than, you know, getting a product report and getting this basically codified?
I guess what I'm trying to impress upon designers out there with simple spreadsheeting using that Eurocode model and looking at some of this test data, kind of convince yourself, at least on one span condition, one proportioning, you can start to calibrate that model. So for your building, you know, something's going to be different. The span might be different. The rib spacing might be different. Performance targets for vibration might be different or non-existent if it's a roof. So you can start to lean on that Eurocode 5 method to really design with confidence, and the right % composite stiffness assumption now that you've seen that adhesive and screw glue we've used. So there's flexibility there, right, for different buildings. And we'll talk if you want to do 60 feet and you know, I mean, and let's say a hospital lab with sensitive equipment, you know, it's like, well, okay, timeout. That might have to go back to the drawing board on some things, but you know, bounding it around the span. I mean, 30 foot's a module we hear a lot about. It lets you start to get underfloor parking on projects without having to transfer beams. It works for education buildings, as mentioned. So I don't know, we can do a few more of these at 30 feet, but let's see where you use your, hopefully I think an engineer can see some of that intuition and knowledge they could extrapolate from this point a little bit to make it work with your project. Doesn't have to be a carbon copy.
Hans-Erik, you mentioned the speed to get from the production into the testing. I mean, Andre, from your end, how long do you need to be able to clear out some space on the lab floor and be able to get some access in there?
Yeah, I would say, I think the conversation started maybe 6 months ahead of time. Hans-Erik, you'll probably remember better. But by the time we got the panels, you know, the lab floor was ready, was ready to go. We had the steel beams that were going to be receiving the ribs. They were there, and so yeah, it just we did a like everything else in this project. You know, it was, I think, done just in time. You know, unfortunately, sometimes we do still take another week or so than what we would like in the testing, just to get everything set up, all the instrumentation. But, you know, to test more or less plus or minus 2 weeks, we were ready to go ahead of time. Yeah.
Yeah, we saw it come in. The schedule shifted a month or two. You know, there's always, so yeah, that first query came in. I remember, Andre, we recognized too that I think it sometimes contracts take some time to sign. So there was the time in there to kind of get the agreement in place. So if you call, it's your item to answer, but I think if things are moving, you could do this in a turnaround as long as you had lab availability space, that, you know, 4-month time frame, right?
Yeah, I think it fits. Yeah, it's 3 to 4 months, and in general, it fits like anything else. If you have a project that's already being developed, you can already foresee that you're going to need some testing. Just start communicating with the labs as soon as possible, just so that it's part of your work model and your workflow as well. Like anything else, yeah, in a project.
Yeah, now you guys have the new lab too, so there might be more space. Not committing you guys to anything, but
Yeah, this is Ian from TDI. I would sort of echo Andre's point about as soon as you think you might need some testing, give us a heads up. We're now in a very fortunate position at OSU because there are 3 high bay structural testing spaces across the campus. But still, you know, there's a lot of research going on. We do quite a lot of contract testing, and we're going to be starting work with our consortium too. So we just advise you always give us lots of lead time. It's always helpful.
Oh, okay.
I had a question for the testing. Was it required to test 3 different panels, or was there different things that you're trying to test in the 3 different panels? Like different data points you're trying to get.
it was just one was the requirement.
Yeah.
You always want a spare, man. You got to have a contingency panel, right? So when you're down there in the lab, test frame set up, somewhere along the way, we rounded it up to 3. We ended up testing the same thing over 3 times. And the long story short is the peak strengths were pretty close. So there is some statistical way, right? In timber connection or timber design, you want to do sample sizes like 28, 30 specimens and start to do the statistics to find. Anyways, you can start to actually do that per one standard at like a specimen size of 3. I don't know, but what we just hinged it on the code. With codes, it's 1 specimen, take your peak load, divide by 2.5. And the commentary of the IBC is very short for this section. It said this is the committee's agreed this is a standardized way to come up with an allowable stress design value for structural members. I mean, so I would actually just wanted a minimum, especially now that this body is here, right? We have 3. If you want to get out a little bit to a different scenario, much more justifiable just to do 1 to fill out that project specific case, right? Because you're building out a bigger data set.
Yeah, I would just add, because the first test was successful, then, you know, we put on the researcher hat for a minute again. And then we said, okay, now what else can we instrument? What else can we do? So we, you know, explore that, but that was not the initial intent. Initial intent was there's 3 specimens so that, you know, we get one test, at least. Sometimes, you know, we just, you know, other projects we've worked just with 1 specimen or maybe 2 specimens, and that's fine. But it was good to have the extra specimens also to then learn more about these rib panels and the performance of the whole double T section.
Very cool. Thanks.
Hey, Andre, this is Todd Byerther. Greetings.
Hi, Todd.
So I think this is really interesting to take it to the lab to do the R&D, especially on these first ones. But you know, my interpretation of Chapter 17 is that you wouldn't necessarily need to take it to a full, you know, ASTM, you know, what I see as a D198 setup there, right? I think it'd be interesting to bring heads together and think of a more practical field application if this route is preferred. You know, to get to 2.5 times the, you know, the design load is not too intense, right? For, you know, for field application. Any thoughts on that?
Can you clarify in terms of you're thinking more about doing field testing?
Field proof loading.
Proof loading.
You know? Yeah, because you know, you don't need to take it to failure under the 1709 criteria, right?
Right.
So I think it'd be interesting to then now kind of correlate between the testing you did in the lab with, you know, some sort of more deployable, you know, in front of the building official, perhaps, right?
Right, on site kind of thing.
You know,
yeah, I mean, if you're trusting, you know, if you're in the stage of your development where you've seen enough literature, enough research that you're pretty confident about how it will perform, then yeah, I don't see an issue at all about doing some. It's done in the bridge world, right? A lot, where you actually deliver projects based on live load testing on the field, and especially for certain bridges. So I don't see an issue. I like your idea, Todd. I think it could be interesting to put heads together and find ways of making that a possibility depending on what you're developing as well. And especially as more and more research and more of these big tests are done, possibly someone can just use exactly the same test results and that's enough. But maybe for other building officials, that may not be enough. So maybe coming up with some in-field, in situ testing may be good. The vibration is being done in situ, but maybe some kind of load testing, maybe with some sandbags or something like that could be used. Yeah.
Thank you.
Or we might have time for one more if somebody's got a pressing question. Well, Andre, Hans-Erik, do you have any final thoughts you wanna share with us? Future projects, holiday plans, anything?
Again, just good to hear so many familiar voices on the call. I'm been working from home for a long time, so and also, yeah, just I said it, man. It's like feels so good to give this talk finally because there's a good story to tell. The university helped us immeasurably, and yeah, we're interested to just good to engage. Free exchange of ideas here in this forum, and here's one idea.
Well, it was extremely interesting. I learned a lot personally, and I'm sure everybody else did. So thank you guys for taking the time to present. We really appreciate it. We'll give you another silent round of applause here. And wish you guys a happy holidays. And, you know, curious to see what you guys are working on a couple months from now, I guess. when we
Thank
touch
you.
meetups again.
Thank
Thank
you.
you.
Happy holidays, guys.
Thank you.
Yeah, happy holidays, everybody. And thanks, Hans-Erik.